All right, lecture 3.8, central moments. Given a probability mass function or probability density function of a random variable, several useful parameters of the random variable can be computed. These are called central moments, which quantify parameters relative to its mean. So the definition of central moments. The nth central moment of a random variable x with PDF f is defined as the expected value of, see there's this difference here, so you subtract out from the random variable its mean value, and then you raise that difference up to the nth power and you take the expectation of that. So that's the way that we write the expected, or the nth moment. The nth moment is just literally using the expectation definition and plugging in that shift and power of it. For a discrete random variable k with PMFF, we have a very similar definition. So, first moment. Let's prove that the first moment of continuous random variable x is 0. Okay? So, from the definition of the first moment, we know that the expected value of x minus mu x, or the mean of x. I've kind of been inconsistent using mu and using m. Raised to the first power, which is the first moment of x, first central moment of x. We get the integral from negative to positive infinity of x minus mx to the first power f of x dx. And we can split this out into two integrals. So we have the integral from negative infinity to positive infinity of x f of x dx, and we have minus we can pull out the mean then, because that's just going to be a constant, mean of x times the integral from minus infinity to plus infinity of f of x dx. Okay. Now, what we look at and see here is that this is, by definition, the expected value of x, right? So the expected value of x is is what we defined our mean of x to be. The integral of a probability mass function over its entire domain is equal to 1, right? So we're just left with mx, and you take the difference and you get 0. So the first moment of a continuous random variable is 0. Always. For everyone. The second central moment of a random variable x is called the variance, and is denoted either sigma x squared or variance of x, or the expected value of x minus its mean squared. The variance is a measure of the width or spread of the PMF or PDF. We usually compute the variance with the formula that the variance of x is equal to the expected value of x squared minus the mean of x squared. Other properties of variance include, for a real constant c, the variance of a constant is 0. The variance of a random variable plus a constant is just the variance of the random variable. The variance of a scaled random variable is just the scaling constant squared times the variance of the random variable. The standard deviation is defined as being the square root of the variance, which, as we can see, works well with the notation for variance being sigma x squared. Although the variance is mathematically more convenient, the standard deviation has the same physical units as x. So, it is often the more physically meaningful quantity. Due to its meaning as the width or spread of the probability distribution and its sharing of physical units, it is a convenient choice for error bars and on plots of a random variable. So, if you're looking for a good candidate for an error bar, standard deviation is a good one. Sometimes people do one standard deviation. That's probably the most common. Some other people will take like 2 standard deviations as the error bar. Okay. Usually you do plus and minus 1 standard deviation. The skewness, skew of x, is a normalized third central moment. Okay, so you take the third central moment and you divide it by the standard deviation cubed. Skewness is a measure of asymmetry of a random variable's PDF or PMF. For a symmetric PMF or PDF, such as the Gaussian PDF, the skew is 0. The kurtosis, or kurt of x, is a normalized fourth central moment. So if you take the fourth central moment and you divide it by the variance squared, you get the kurtosis. Kurtosis is a measure of the tailedness of a random variable's PDF or PMF. Heavier tails yield higher kurtosis. Okay? So that's like when the probability density function trails off. Is that trail off fatter, or is it really skinny? A Gaussian random variable has PDF with kurtosis 3. Given that for Gaussians, both skew and kurtosis have nice values, so the skew is 0 for a PDF, for a Gaussian, and the kurtosis is 3, we can think of skewness and kurtosis as measures of similarity to the Gaussian PDF. So that is a common thing to do, especially when you're looking at a measurement, and many noise processes are fairly well modeled as being Gaussian noise. And if you're expecting only, nice Gaussian noise like thermal excitation of your circuits and whatnot, and you check to see what the skew and kurtosis are for your actual measured values, which is something we'll learn how to estimate later from actual data instead of from a probability density function. What you can do is you can see, like, is this very Gaussian? Is the skew near 0? Is the kurtosis near 3? And if they're not, then you can say something else is going on here. This is not just random noise. This is not just like thermal excitation in the circuit. There's something else going on. There's some other process that's not Gaussian that's present. It's not to say that when you have Gaussian noise that it's just thermal excitation. It could be some other noise process that's Gaussian. But it's really nice when you're doing a very precise measurement, especially, to check this. So I've done experiments where the noise that comes in is thermal noise, thermal excitation, unless we have, like, for instance, there's a cryogenic fluid that we flow through the apparatus, which is liquid helium. And liquid helium is very cold and it cools down the experiment, the apparatus. Well, that flow of that liquid helium can cause a sort of whistling, or like a little bit of noise, a sort of flow noise that can happen. And it does not look Gaussian at all. So sometimes there'll be like a little bit of water vapor that got in there and it like turned into ice, and it'll cause some sort of restriction on the nozzle, and there'll be this like whistling that'll happen. And so when we run those experiments, we check to see, is the noise looking Gaussian? If it's not looking Gaussian, there's probably some other noise process here that's going on, like that whistling, which might happen at a certain frequency, for instance. So we would look at the noise process to see what's going on. Yeah, so we would want to say, okay, if our measurements are good, we aren't expecting any noise processes to enter that aren't Gaussian. And so if you have a noise process that's not Gaussian that's going on, you don't know what it is, you can't explain it, then you might have cause to worry about the validity of your measurement. So great. So that's central moments.